Welcome to Statics and Strength of Materials. Today we'll be covering Lecture 4 and we'll be discussing how to approach problems and how to approach numerical accuracy. Computers are typically used in analysis of a lot of engineering problems, and examples of that would be finite element methods, computer-aided design programs like AutoCAD, SolidWorks. In this kind of programs, we ought to be cognizant on how to approach different problems, how to account for numerical accuracy properly. One of the things we need to be doing in engineering is to do all the work in a very neat way, step by step, explaining your steps. Because when you are clear about what you're doing, not only you may find errors in what you're doing, but it's going to allow you to think more clearly about how to approach a problem. So being disorganized in engineering can be a problem. It can lead to some errors in your numerical calculations. So I encourage you to be as organized as possible as you do these engineering problems, and that entails writing step by step what are you doing, why you're doing it, and the questions that follow and where they come from. It's very important also to ensure your units are consistent. If you're in SI units, try to make sure that all the units are consistent per what we had discussed previously. The approach to solving problems in engineering is to really understand what the problem is asking for you to do. You want to understand the inputs that were provided, the given data, the known data, and what is being asked from the problem. You may want to also make sure you understand the figures very well, because if you do, then in combining that figure with the problem statement can actually help you solve the problem in a more straightforward manner. I encourage you also to make assumptions. There are times that not all the data is known, and so you may have to go through additional resources in real life engineering problems and make assumptions about that data. And that may entail researching papers, looking at books, what others may have done in your similar situation. But it's important that all the steps are well defined in your problem statement. The free body diagrams are spatial diagrams that we'll be discussing in a very next lecture, and they allow you to understand how the load paths are getting transmitted through a particular component. And that will help you in solving a lot of these static engineering problems and mechanics of materials. It's also important to understand the fundamental physics that will drive that problem statement, that problem that you're working on. And that can mean, what kind of physics are you encountering here? Is there object in rest? Is it motion? Um, and what are the proper equations that need to be used to solve for unknown quantities? I also encourage you that every time you approach a problem and you solve it, that you do some sanity checks, some solution checks. Test for errors by verifying that the units of the results are correct. Test for errors in making sure that if you didn't use certain equations, and if you were to use them, can you verify your results in alternate manners? Also apply experience and physical intuition to assess whether the results seem reasonable. There are many times that your results may not look reasonable, and it could have been an error in your assumptions, in the units, or even your own calculations. And it's important that you spend time developing discipline in this area, because a lot of the failures that occur in real life can be traced back to fundamental behaviors in solving a problem, being disorganized, using inconsistent units, making assumptions that are not founded in reality, um, making errors in calculations. We're all humans. So making sure that you're organized and that all your assumptions are clear. And in addition to that, I encourage you to always have a peer review. Somebody else check your work so that you can then determine, did I make an error, error in judgment? So I encourage you to follow those steps because that's going to help your career moving forward. Many engineering problems can be simplified to enable applications of physics-based principles. You may have to use enduring judgment to make assumptions, to justify the assumptions. It's important that the statement of the problem that you're trying to solve be clear and precise. It should contain all the data you need, but if it's not there, you may have to make assumptions, and we just discussed that. Um, Also, make sure you can translate the problem into a neat drawing that shows all the quantities that should be involved in the problem. And then finally, like we discussed, free body diagrams may be important, and I'll be discussing that in the very following lecture. Another area I want you to keep in mind is numerical accuracy. The accuracy of a solution of a problem depends upon two items: the accuracy of the given data that was provided to you and the computations you're performing. The solution cannot be more accurate than the inputs to the problem. For example, if the loading of a bridge is known to be 75,000 pounds plus minus 100 pounds, give or take, the relative error due to this plus minus 100 pounds is in the order of 0.13%. So if you were to calculate reaction forces on a bridge support, it would be very meaningless to report 14,322 pounds as the accuracy of the solution because the solution cannot be more accurate than 0.13%. So one way to show the answer is to say, the answer should be 0.13 divided by 100 times 14,322 pounds. And so you know that the error cannot be larger than 20 pounds. And so you may want to report your answers as 14,320 plus minus 20 pounds. So it's important to understand the uncertainty in the data, the bounds of the data that's going into the problem, and that your solution be a little bit more, if it's too accurate, more accurate than the inputs to the problem, that's an error. You want to have bounds to your solution given inputs to the problem that have a band of uncertainty. Data are seldom known with an accuracy greater than 0.2%. Typically, even less than that. So it is unjustified to write results with accuracy greater than 0.2%. A practical rule is to use 4 figures to record numbers beginning with a 1 and 3 figures in all other cases. As an example, a force of 40 pounds should be represented as 40.0 pounds, and a force of 15 pounds should be represented as 15.00 pounds. That's just a rule of thumb, but in general, you just don't want to be more accurate, um, you know, compared to the accuracy of the inputs to the problem.